Hi, welcome back to this video series on cryptography. In the previous segment, we talked about how to construct a pseudo-random function. In this segment, we will make use of that construction for encryption and decryption purposes. One naive approach would be just call the pseudo-random function f and evaluate at point m. Okay, if m is your message, right? K is your key, m is your message. By definition, pseudo-random function will not leak information about m, okay, because it's going to give you some random looking output. So it may seem natural to directly instantiate a pseudo-random function like this, right? However, this is not going to be correct, not going to be secure. Let me show you with an example right away. So let's say let's take this example. Let's say we have a 256-bit random key. We generate a 256-bit random key, and our message is say some number. Let's say another 256-bit number, which is 2 power 56, right? This is 2 power 256. Okay, that's the message. Now let's do f key and a message. Okay, this is a pseudo-random function, right? We get some gibberish. So let's print the gibberish and see what happens. So we get some gibberish. We were trying to encrypt the message, 256-bit message. We get some gibberish. We can encrypt again. See what happens. Okay, there's a problem here. You see here, the first output ciphertext is the same as the second output ciphertext. Okay, that means one can infer that the message must have been the same. So if we encrypt the same message 2 times, we get the same ciphertext. That's not good. Okay, so the problem is now, let's go back to the whiteboard. Why is the problem? Well, the problem is, it's clear from the ciphertext we can tell whether say we are given 2 ciphertexts, right? In this case, it's C and C 2 times. So we know for sure that means the message M must have been the same. Same message encrypted 2 times using the same key is not good. Okay, so from that, therefore we should not be using this construction. Okay, so how do we fix this problem? It turned out that we can easily fix this problem with a small trick. Okay, let me explain this trick now. First, we generate a random number R, right? And we apply pseudo-random function on a random number R, okay? So it's going to give some gibberish. So we first generate a random number R. We feed this R into our pseudo-random function F, parameterized with K, right? K is the key, secret key. In the previous construction, we talked about how to construct that function Fk. What you get out is some gibberish, right? And here is your message. Suppose I have my message, okay, in binary, 0s and 1s, right? And so on. All you're going to do is you're going to XOR your message with your output of the pseudo-random function, and that becomes your ciphertext. It's exactly the same idea used in counter mode, GCM, and many constructions use this idea. So here is your message, and here is your ciphertext. Okay. Why is this construction secure? This construction is secure because R is randomly chosen, and the pseudo-random function by definition will give you some gibberish random here, random output, some other random output, and that we usually call that as a key stream, right? You have a stream of bytes, and that you encrypt with your message stream or stream of bits, and you encrypt. Encryption is basically happening here in this box, right? You encrypt your message with the output produced by the pseudo-random function to get the ciphertext. Okay, and now this is the construction for encryption, right? So how do we decrypt then? For decryption, we need actually the same circuit. If the encryption algorithm outputs two things, a random number R and the ciphertext C, the same circuit can be used to decrypt, okay? And let me explain how that will work. We use the same R, we run the FK of R again, which is going to produce the same key stream because random functions by definition are deterministic. So you will get the same output here. The key stream will be the same. And now, only difference is instead of putting a message here, you will be putting a ciphertext here, the ciphertext C. You will XOR it with your ciphertext, and your output of the key stream, what you will get out is the message stream now. The message is going to come out. That's all. That's the idea of constructing a block cipher from a pseudorandom function. Okay, so all we did is, let me write it in notation. First, the encryption algorithm works as follows: generates a random R, right? Calls the FK of R to produce some key stream. Okay, this is the key stream. Let's call it KS or KS, yeah, key stream. And then the third step, we produce the ciphertext by taking the key stream, XOR it with message. Okay, I'm going to make some assumptions here, of course, because XOR only works if the corresponding bit vectors are of the same length. So I'm making an assumption here. My pseudorandom function F takes an n-bit key, right, and an n-bit key as well as an n-bit data point, and gives you back an n-bit random looking. But what I mean by random looking is it's not distinguishable from a truly random function. Okay, so this is the assumption I'm making here for the function F. Okay, so this is the encryption algorithm, and the output of the encryption algorithm is a pair. The pair is R and C. Okay, the decryption algorithm is extremely simple now. All we are going to do is do the same. Step one, generate the key stream. Of course, the encryption and decryption should know the same key K, and it will now produce the same key stream KS that was produced here, because the inputs are the same to this function. And then we take the key stream, right? We XOR it with ciphertext now. Because of the XOR property, if you XOR this number, equation number 3, on both sides by C, the C and C on the left-hand side will get cancelled out. You will get a M back. So let me clarify that. Maybe I was wrong. We do XOR on both sides by KS. So KS on the right-hand side will get cancelled out. So you will be left with the M, which is what we need to recover. Okay. So that's all. Now we got the message that was encrypted. The same message was decrypted here. Okay, so there are some important details I need to tell you. Why is this secure? If you encrypt the same message 2 times, why would this not leak that information? It won't leak the information because we generate a random number R every time we call the encryption function. Okay, therefore, same message will be encrypted into different ciphertexts. Okay, of course, there is a theoretical limit of how many times can you do this, meaning how many times can you use the same key K to encrypt a lot of data. I'm not going to talk about the fine-grained details, but you can imagine this particular construction, which encrypts only one block, is secure for about let me give an approximation. Okay, suppose you query this pseudorandom function, say q of n times some polynomial in n, right? As long as this ratio is negligible, you're good. Okay. If you don't understand this is perfectly fine. So say your n is, for example, 128-bit number. Okay. So this construction is telling us that If you want this ratio to be negligible, say negligible means usually 1 by 2 power 32 or something like that, you can play different values of q of n and try to figure out how many blocks can I encrypt using this construction. Okay, I will talk about the theoretical analysis later, but at this point, what is important is that this construction is a straightforward application of the concept of pseudorandom function to hide the fact that the same message is encrypted 2 times. You will get 2 different ciphertexts. Okay, this is the fundamental idea used in the counter mode with some modification. Okay, in the counter mode, we will be instantiating this idea multiple times for multiple blocks by taking R and then R plus 1, R plus 2, and so on. Okay. Anyway, let me now show to you a demo of this idea quickly. So what we are going to do now is encryption decryption algorithm that I just talked about, and encrypt the same message 2 times to show to you the outputs are different now. So I'm going to call the encryption function, which is going to encrypt the data. Okay, which is 2 power 56 is the data that I have, right? Is nothing but 2 power 256, right? So it's which is 256-bit data. Okay, and we will now, well, let's encrypt. Encryption function returns 2 things. One is the random number R, another is the ciphertext. Okay, so we can call it C to be easier to read. So you get ciphertext and the random number R. Now we will let's print the ciphertext. Print the ciphertext C. Okay, let's do the same. Let's do decryption first, and then let's decrypt. Decryption requires the key, a random number, the same random number, and then the ciphertext. Okay, let's print this first. Okay, we should be getting a 2 power 256. It's a very large number, but I'm going to show to you. Maybe I should use an assert. Assert. We decrypt, and we argue that the decryption is same as the encrypted message. Okay. So let's first try this to make sure our decryption works. Yep. Otherwise, we would have gotten an error message, right? Let me just put a not of message. So now you will see something wrong. Yeah. Assert failed. That means the message is same as the decryption. Okay, that's good. Now let's do one more thing. Let's focus on the duplicate part, meaning encrypt the same message 2 times and show to you that the ciphertexts are different now. Okay, I'm going to encrypt the same message, right? 2 times. And I wanted to show to you this is ciphertext 1 and this is ciphertext 2, but the same message didn't change. Okay, let's see whether the ciphertexts are different now. Yep, you see here the ciphertexts are different. We have something here like this, say like this. So somebody who's wiretapping the channel wouldn't be able to tell whether we sent the same number 2 times or 2 different numbers. So that's the idea of this chosen plain text aware security. Okay, let me be more clear that what the kind of security that we are getting here is CPA aware. Okay, CPA means chosen plain text attack aware. Okay, so sending the same message 2 times will not be observed on the channel because the ciphertexts are different. Okay, there is one caveat I need to tell you. This particular construction is not secure against chosen ciphertext attack. So somebody flipping the ciphertext can, suppose I flip this bit, meaning if I flip this bit, this particular bit will also be flipped when the decryptor decrypts it. That can be solved by using a MAC. We will talk about that later. So at this point, what I wanted to show to you is a construction that is secure against eavesdropping and secure against the chosen plain text attack. The novelty of this construction is that it uses a pseudorandom function f for both encryption and decryption, right? And it hides the fact that the same message is encrypted 2 times. Okay, and never use k of m directly. That's not good. Okay, this is the classical problem with the ECB mode. There may be some cases where you want to use this, but in general, you want to avoid this. Okay. All right. That's all. Thank you very much for your attention.